Well, good afternoon, everyone, or good morning, depending where you are. This is Rob Thornton. I'm the President and CEO of the International District Energy Association. It's my pleasure to welcome you to the IDEA webinar series today. We'll hear from Gordon Judd, General Manager of Energy Center San Francisco, Clearway Energy. Gordon will be sharing with all of us how do you reduce potable water use in a district energy system by 80 million gallons per year. Before we begin, let me just walk through a little bit of housekeeping. So the webinar will be recorded and will be available as streaming. The slides will be available to people that have registered in PDF form. We're scheduling about an hour, including time for Q&A at the end. All of the participants on the call, aside from the presenters, are muted. So if you have a question or comment, please submit those in the Q&A box. You see that on the lower right-hand side of your screen, Q&A. So we'd ask you to submit those as the presentation is underway. And then when Gordon is concluded, I'll moderate and manage those questions. We'll try in the sequence they were submitted, and we'll try to get to all of them. We can extend the webinar beyond 1 hour if need be. If you're having problems either with seeing the slides or the audio, please send a note in the chat box function. That's also on the right-hand side. You'll see the chat box. There's a pull-down, and you can chat privately to Cheryl Jakes. Cheryl's my colleague here at IDEA, and she can assist you. Or if it's easier, just call into our office at 1-508-366-9339, and we'll do our best to assist you. At the conclusion of the webinar, there'll be a brief survey. We'd ask if you wouldn't mind just filling that in. And then all of you who are registered will be receiving a link soon after the conclusion that will give you access to download the presentation or visit it in a streaming format after the fact. So you can share it with colleagues if you so choose. One thing, we're really pleased to recognize Clearway Energy and Gordon in particular. They were the recipients of our 2019 Innovation Award. This is a very interesting project, and this past year we had a record turnout of submittals for our IDEA Innovation Award, but there was unanimous support for this particular project, and I think in the next half an hour or so, you'll learn why. But the IDEA Innovation Award, it's an annual event, and really what we're looking for are projects that are innovative and unique, and so they're deploying some maybe new technology, but they should and must be, in fact, operational and sustainable. So it isn't a theoretical presentation, it is a real-world innovation. We like for these, and they get scored on, the submittals get scored on all 4 of these categories. We like for them to be replicable, not necessarily a project that would only have a singular application, but like the project here at Clearway in San Francisco, it could be deployed in other locations. And then finally, you know, a very important aspect is are there economic and environmental advantages from this innovation? Those are obviously attributes that we're all seeking. And the Innovation Award, IDEA, we're really looking to recognize great work that happens among our members, both operating systems and our business partners, the consultants, the manufacturers, suppliers, you know, people that really do bring these interesting projects to reality. So now it's my pleasure to introduce Gordon Judd. Excuse me, Gordon is the General Manager of Clearway Energy's San Francisco Energy Center. They provide district steam to over 170 buildings in downtown San Francisco. Gordon received his Bachelor of Science in Mechanical Engineering from Cal Poly at San Luis Obispo, and after graduating, he served as an unrestricted line officer in the U.S. Navy Submarine Force. He completed his nuclear engineering officer qualifications before separating from the Navy, and then after the Navy, Gordon received his MBA from Golden Gate University, and he's been in the energy industry for 25 plus years in a number of positions, including plant manager, marketing manager. He's been responsible for development and has spent nearly 25 years directly in district energy. So I'd like to thank Gordon in advance. And Gordon, I'm going to give you the ball so you can take it from here.
All right. Thanks a lot, Rob.
A presenter. Here we go. There, you got it. All yours,
right.
Gordon. Thank you.
Thank you, Rob. And thank you to everybody who's chosen to join us. As Rob said, either good afternoon or greetings to wherever time zone you're coming from. I'm going to blaze through a presentation, hopefully in a half hour or less, and the idea is to leave a lot of time for Q&A about how this may apply to your systems or tangentially to other aspects of the project. Let's see. So a quick agenda. We're going to kind of look at these steps, the setup, the opportunity, the design, the execution, extensive results and lessons learned, and then we'll go to Q&A. So first off, Rob introduced this as how do you save 80 million gallons? Well, before we get into the how, kind of really should ask how much is 80 million gallons? So one way of thinking of it is if you take the largest ocean-going oil tanker that fits through the Suez Canal, that's about 50 to 80 million gallons. If you want to put it in the context of, say, 55-gallon drums, if you had a bunch of 55-gallon drums and you laid them end to end, that would be about a 1,000-mile pipeline that you created, and that's about 80 million gallons. And to put it in the more context for the more athletically inclined, that'd be about 120 Olympic-sized pools. So no matter how you slice it, no matter which metric you want to use, 80 million gallons is a lot of water, and it's especially a lot of water here in San Francisco. If we look at what our total usage on an annual basis of water is, we're a once-through steam system. We're right on the area of about 100 million gallons a year. So when we talk about 80 million gallons, that's a large percentage of our total water usage. So as we look at the setup, what is the nexus of how this project came together? Well, it starts with a local subway station, local meaning about 800 feet from our existing plant. And that subway station has a constant, for the last 40 years, intrusion of groundwater into the subway. Subway is about 60 feet below street level. And about 30 million gallons comes in, they collect it in a cistern, and they've pumped it to sewer for 40 years. And as most of you have probably heard over the last 5 years, California has been drought land. And so recently in television and news stories, it's come up that, hey, this subway entity is pumping all this water to sewer and it's being wasted. How we got involved with the subway entity was actually my distribution manager, who was having problems with manholes flooding water from below. And when he met with the subway people, he found out that they were waterproofing their tunnels, and it was preventing water from getting into their tunnels, but it was backing them up in our manholes. So that's really how the genesis of the project came out. If we look at the district energy in San Francisco, one of the aspects is, as I mentioned, we're 100 million gallons a year. That makes us actually one of the largest water users in San Francisco. And as sustainability is becoming a bigger thing, we were kind of feeling like there was a target that was growing on our back with our high water usage. And so we needed to do something to address that. And in addition, not is it just that we're a large volume water user, the costs of that water have gone up a lot over the last 10 years. The city of San Francisco issued a $3.6 billion bond to rebuild the water system, make it seismically stronger, and the cost for that $3.6 billion bond gets passed on to the rates. So maybe 14 years ago, my water costs were water and sewer costs were $250,000 a year, and last year they were $2.2 million, so basically 8 times. And then the city of San Francisco has been also looking for ways to use to do water conservation, water recovery, and this project actually kind of met that wicket as well. This is just a diagram to show you 2 things. On the yellow at the top, that's our water usage over time. So in essence, we've been adding condensate return. We've been getting more efficient with our water usage. So you can see over time, water use has generally been trending down. But when they passed that bond in 2003, you can see on the blue bars, that's our water sewer cost. And you can see how much that's gone up over time to where last year it was, as I said, about $2.2 million. So this presented the kind of the economic driver to actually make water recovery work, because one of the things that you'll see in this presentation is water recovery and water processing is not cheap. As a business in San Francisco, this graph, not to get too focused on anything, this is generally our hard cost to make steam. Blue is gas. You would expect that to be the biggest portion, but what's kind of different for us as a lot of systems is that the red over here, that's our combined water sewer cost. Fully 25% of our total cost to make steam is in the water sewer component. And again, economic driver to do a project like this. One other aspect about this graph that I should point out is that of that red, water plus sewer, the sewer is about 2/3, the water is about 1/3. And the reason I point that out is that'll be critical as we talk later in about how we decided on technologies and things like that. So sewer cost is a huge cost here in San Francisco. So the opportunity, the Powell Street Station is the one I talked about where all this water is available, and it's about 2 blocks from us, about 800 feet. The San Francisco Public Utility Commission, they're the ones who run the water and sewer system. They were actually offering grants to do water reuse projects of almost any size, and they were offering up to $500,000 for a large water reuse project. And then the big question in this project, was there a way where a private company like or Clearway Energy could work with public entity, and actually in this case it's 2 public entities. The public entity, the City of San Francisco Water Sewer System, and it's also the state agency which runs the subway. Is there a way to bring all 3 of those entities together for a project that would actually work and benefit everybody? So here's the concept. The concept is that we would engage, Clearway would engage the San Francisco Public Utilities Commission, we'd engage the subway entity, and we would do a project collaboration process to say, hey, there's wins for everybody in this. The idea would be to recover the 30 million gallons of water from the subway station and figure out a way to bring that to our plant about 800 feet away. The other thought that came along as we kind of developed the project concept was, well, if you can recover water and groundwater intrusion to a subway station and process that for use in boilers, what about the idea of doing a well? Now, this is kind of a radical idea because San Francisco hasn't permitted a production well in over 40 years. So there's nobody within the various agencies of the city that actually knows how to do that. And so that's been a interesting addition to the project, I'll call it, adding a well. But the goal was this, is essentially reduce our potable water usage by 80%. So if we say in 2016 we make up 90% of our water for our plant, the other 10% we have some condensate return that comes in and some other water recovery going on. But the goal is that by 2026, in a decade, that we could be to a point where we use 0 makeup water from the city. And, of course, the folks at corporate would really like a project that actually had a payback, so we targeted a project that would actually pay back in 3 years. So just a quick overview of where the project is. So down in lower right, here's where the subway station is. This is the corner of 5th and Market. Bloomingdale's to the left. San Francisco Mint up here. This is a major intersection of downtown San Francisco. And what you see in this outline on the orange is where we ran the pipeline from the subway station up 5th Street and then down this alley to our plant. And I think total run there is it's 800 feet as the crow flies, turns out to be about a 1,000-foot pipeline. This part was actually fairly easy because we're already equipped to run piping in San Francisco. Also, the thing that made this easy is that the current subway station, they have their cistern, 60 or 70 feet below street level, and they already have pumps installed in that cistern. And what the pumps do is they pump the water almost straight up vertically, and then it turns right and goes into the sewer. So they already bring this water up out of the station, and really what we had to do was just tie into the pipe that goes to the sewer. What we ended up doing was actually putting in a three-way valve so that the water could be either directed to the sewer or directed to our plant. Not to get too much into process engineering, but this is really how the process flows. What I really want to show on this diagram is kind of a couple things. One is the black dotted line across the center. Everything below the line is what I'll call existing plant, so that exists in our plant today. And essentially everything above the line is newly installed equipment. And one of the things you'll see is that there's several places where the process crosses the line. So from raw water to the softeners was across, from the softeners back to the reverse osmosis is a line. And the reason this is critical is because one of the biggest challenges, and we'll talk about in the lessons learned, is that the hardest thing with this project was integrating a new high-tech, high power demand system into a very aged plant. Our plant is over 100 years old, and some of the electric systems and piping systems reflect that. And so we ran into a lot of challenges after we commissioned the system. The one other aspect I'll show on this diagram that's relevant to the future discussion is in this lower right. Our plant being a once-through steam system, we utilize a direct contact economizer. For those of you not familiar with that, what that means is that the water that we're going to send to the boilers before it goes to the deaerator, it actually goes into a mixing chamber where the water is sprayed down and the flue gas from the boilers rises up from the bottom, and there's a direct contact between the two. You get about a 7% gain in heat from that, meaning 7% reduction in gas usage. And this is critical. It's not a system most of you would have out there, but it's critical because this created some other challenges for us in implementing this system and actually continuing to operate it. So having direct contact, you've got makeup water going to the deaerator that has directly mixed with the flue gas of the boilers. This is just a quick kind of how big is the system we're talking about. You don't see it in the photograph. So this is a kind of an engineering diagram that shows the major components. On the left side, you have the raw water coming in from the subway station. That goes into a receiving tank. And then the first thing it goes through is what we call a microfiltration. So this is what you would commonly see as a cargo container, 40 feet long, and the inside is filled with water treatment equipment. And this is where bulk filtration is going on. It's removing solids, removing oils, removing basically the solid stuff from the water coming from the subway station. This tank where we receive water also receives the well water that we're installing as well. So this is kind of like, if you think about it, pre-filtration. What you don't see on this diagram is the water leaves the microfiltration from the process diagram previously, goes to our existing plant, goes through water softeners, very typical sodium zeolite softeners, and then that actually removes hardness, calcium and magnesium primarily. Once that's done, it comes back over here and goes to the reverse osmosis trailer. And this is a longer, kind of a stretch cargo container, as it were, about 52 feet long. That's where the real magic happens. That's where the water is really cleaned up to better than boiler standards. And that's where all the magic is happening. And then this large tank over on the right is where that water is collected, and then we have a pumping system that takes that out to the plant. If we look at the execution of the project, there was a couple things that made it basically feasible to do. All of the steel work, so like over on the right, you see this structural steel framing put in to receive the equipment. That was all constructed by employees on site, pipe fitting and welding. The other thing that made it critical was most of the heavy components in terms of water treatment, both microfiltration and the RO systems, those were modular design. Those were built off-site by the vendors, and then they were brought in-site and then use a crane to put them in place. So that really minimized the on-site time and cost of doing construction in San Francisco. It's very expensive to build here, so being able to bring this equipment in modularly was a really key element of the project, key part of the success. When we look at the results, what did we end up with? So the total project cost for this, and this is just for, I'll call it the BART water system or the subway system, it's about $3.5 million. We expect to get a total annual savings of about $1 million a year, so that'll give us our 3+ year payback. This breakdown of the savings is about $800,000 a year on the water sewer savings. And then because we're using reverse osmosis technology, essentially we're ending up with a lot cleaner water going to our plant than we've ever had before, meaning that most of the alkalinity is stripped out, and our system uses a lot of amines to neutralize the carbonic acid created from the alkalinity. And with the reverse osmosis, we're going to have a lot less alkalinity going into the boilers, and so our amine usage is actually going to go down. So we'll actually have a lot of chemical savings on the back end. We were approved by the SFPUC for the full $500,000 grant. They were very excited about this project because they had water saving goals going up through 2025, and when we brought them this project, essentially in one step, we would get them to their 2025 water savings goal. And so they approved us for the full $500,000 grant, which was the largest they could offer. I talked about a well a little earlier. Essentially what the idea was is, hey, if you're doing this cleanup on this groundwater, why not add a well? We investigated that. We did some geotechnical assessments, and lo and behold, it looked like there was actually well water available. When we installed it, it looks like we have a well that produces about 200 gallons per minute, and it really was only about a $250,000 add on the $3.5 million project. But yet, the subway water was about 70 gallons a minute. So if you look at adding the benefit of adding a well, and the water quality was almost the same, is that it made a great enhancement to the project economics by adding a well. Now that well, I tell you right now, is not fully permitted. It's installed. We're running it as kind of a testing mode right now, and we're literally believing any week now we should have we've crossed all the hurdles with the city, and we think we have all the requirements to get a well permit, and so we're expecting to see that in the upcoming weeks. One of the things that, in terms of, as we look at an old district energy steam system, a once-through steam system, is having this recovered water be part of our steam makeup. We're actually looking at being able to develop and market a new product called sustainable steam. We think because it's recovered water, that it's available for lead points, and we think that that'll have additional marketing ability for us. This is nothing that was worked into the payback of the project. We think this would be like icing on the cake as we go forward. So when we looked at that graph earlier, this is what we showed earlier. Here's what we anticipate our water costs and our water consumption from the city are going to do as a result of this project. It's not a straight drop, and then the reason is, as I said, the integration of this with our existing plant has been difficult. And so, matter of fact, we have the vendor at the plant this week doing some program modifications to make our recovery more efficient. So we believe over time we're going to be getting down to where we're only using 10% in coming years, and then it'll be additional projects that actually drive this to zero, as I talked about earlier. But you can also see on the blue lines what the cost is. Up here, last year, $2.2 million, and we're expecting our city water cost to go down to something less than $1 million, maybe even less than $500,000 a year. So that's a big water sewer savings for us. Lessons learned. First lesson, talked about it. Integrating new equipment into an old plant is really hard. We have an engineering company who was involved in doing the project for us, and they looked at a lot of things, caught a lot of things, and then there was things we could have never conceived of in terms of existing switchgear that's rated for 1,000 amps not actually being able to deliver 1,000 amps. Old conductors failing, when they were put under load. So we just had a lot of challenges on the electrical side. The water treatment system has lots of pumps that start and stop. Both the microfiltration and the reverse osmosis, they basically run as batch systems. And that's a lot different than traditional filtration. Most traditional filtration runs as kind of a constant throughput, and these ones run as batch, and I'll talk about later why that is. And we also have on-site electrical generation with our cogen plant, and these high starting and stopping currents were causing havoc with the cogen plant, and we had to basically reorient how we run the cogen, and we had to shift away from efficiency and had to shift it more towards reliability. And then the other one that's been a little bit of a lesson learned is running softened city water is a pretty tame type of water to run through carbon steel piping. Water that's been run through a reverse osmosis is ultra clean. It's actually so clean you can't even drink it, because if you drink the water, it'll actually pull minerals out of your skin and it won't satisfy thirst. It's really interesting. But in carbon steel piping, what it creates is a tendency for ions to want to leave the carbon steel pipe and jump into the water and try to make it, less pure. And so we've had a couple small locations where we had some remnants of carbon steel piping where we've seen a significantly accelerated corrosion. And so we're replacing those with stainless steel. All the other new piping that was put into the system was all stainless steel, but these are some existing plant ties. Oops, sorry, wrong button. And then the other significant plant change that we've had is because we're running well water and subway recovered water going through microfiltration, that's a lot more hardness. And so our existing water softeners are having a lot shorter runs, and the operators of the plant have had a hard time adjusting to that because typically a softener would run for a week before going hard. Now they're running for like a day before going hard. So it's required, increased salt deliveries and other things. So that's been a new one too. Lesson learned number 2, not what we expected in subway water. So as you would imagine, as we're scoping out this project, we took multiple samples from the subway cistern to say what's the water, how do we have to treat it, and whatever else. Well, the one thing that we did is when we took those samples, that was using the existing pumps in the cistern. And part of our project putting in that new pipeline, we had to change out those pumps to provide more head, and it turns out they also take more suction. Well, what happens is they also suck a lot of stuff off the bottom of that cistern. So these are some things that came through after we did our analysis and we had planned for what we thought was in the water. These are some things that came through the pipeline from the subway station to our plant. And the pipeline is a 8-inch pipeline, and I didn't think it would happen, but you can actually have a full-size bottle make it through. There's hypodermic needles, and there's a lot of shredded plastic. So this is like plastic bags that end up in the railway trains, and then they get washed down into the cistern, picked up by the pumps, chewed up. And this system was not put in with the anticipation that we would have to deal with anywhere near this level of solids. So we were having a lot of problems with the clogging of strainers and things like that. So we had to essentially on the fly kind of make our own strainer system to take out these bulk problems. Lesson learned number 3, chemicals. Lots of chemicals. Water treatment takes lots of chemicals. It's not just straight filtration, because to make the filtration work, it requires a low pH here, a high pH there, chlorine to get rid of biologics, and a lot of things. So, here's just a quick picture of, all of these are new chemical tanks that we were added to our plant as part of this process. To put it in list form, here's the chemicals we used to run the plant with before we had the reverse osmosis. These are 3 boiler chemicals that probably everybody is familiar with. Well, here's our chemical list after having the reverse osmosis systems, and you can see there's a whole batch of new chemicals required. And this makes the system run good and right, but you do have to allow for provision of a lot more chemical treatment, a lot more chemical deliveries. Lesson learned number 4, chemistry is different. So not just chemicals, but the actual water chemistry is different. So we talked earlier about what happens when you have demin water going through carbon steel piping. We already know that. You get a lot of corrosion. Even with a neutral pH of 7, you still get a lot of corrosion. But the other thing is, remember back on the process flow diagram, I talked about direct contact. So our water used to go through softeners, and then it would go into the direct contact system. It would spray from above. The flue gas would come up and mix with it, give up a lot of heat, and the water would leave at about 150 degrees, and all was good. Well, what we found out is that the chemistry inside direct contact changed when we started introducing demin water. And essentially what happens is with softener water going into the direct contact, there was alkalinity still part of the water. Well, the alkalinity buffered or prevented a lot of CO2 from being absorbed. It was a kind of a equilibrium equation, as it were. Well, once we run water through there that's demin, it has no alkalinity in it, and now running through the direct contact system, it has a high affinity to absorb carbon dioxide from the flue gas. And so that was a change. And so now we were seeing, downstream pH problems going into the deaerator and some other places. And so we think we're getting into the process where we're going to convert the direct contact system to an indirect contact system and basically keep the demin water separate from the flue gas directly and prevent the CO2 absorption. Lesson learned number 5. Essentially, after all of what I've talked about, this has all worked out actually better than we thought. Adding the well was totally the right thing to do in terms of where you're getting a lot of water capability from the well, probably tripling the amount of water reduction we get. And then in the RO, specifically, I talked about this earlier. Remember, our sewer cost is probably 2/3 of that water sewer number that we were talking about. And so one of the things as we were evaluating technologies to do this is we were very concerned with an RO and how much permeate and how much discharge there would be from the reverse osmosis systems. And we ended up going with what is essentially a new reverse osmosis technology. The reverse osmosis membranes and everything, that's all standard. It's the same ones that people are very familiar with. But the Desalitech uses a different process. It's a patented process. And what it does is it allows a much higher recovery. So what we're seeing, I just actually checked at the plant this morning before I came over, we're seeing with our reverse osmosis system that we're actually recovering about 87% permeate. And that means we're only basically of the water cleanup we're doing, only about 13 to 15% is going to sewer. And that's a huge driver for us on the economics because the sewer cost is so expensive. So with that, I think I did meet my goal of under 30 minutes, and I would guess open it to Rob to open it to any questions that anybody has.
Thanks, Gordon. Well done. Really appreciate it. So we do have a couple of questions. So the first was the attendee asked, RO reverse osmosis is generally understood to be quite energy intensive. Does that add to the parasitic losses? Did you, in your economic analysis, did you calculate the sort of cost of operating the RO system?
Yes and no. We calculated the electric cost, but on our internal plan analysis, it looked like we had a lot of room on our cogeneration system. So we were planning that, we've got room on our cogeneration system. Cost of that electricity is very low because we recover substantially all the heat. And so we said, we're golden, it's going to be minimal impact on electrical. What we didn't account for was the large size of the starting and stopping loads. And in this territory, we're not allowed to export electricity at all. And there's a safety on the front end of the plant where if we start or if we get close to exporting, it trips us or islands us from the utility, which happened. And the cogen is supposed to continue to run on that, but then all of a sudden you've got all this extra generation and the system hasn't had time to dial back yet. And what would happen is we'd island, and then we'd trip offline. And what was happening is our own cogen supplying this higher load was causing reliability issues for the whole plant. So that goes to where I said we initially changed the cogen operation for reliability instead of efficiency. And now as we've got the water process online, we're going back to moving the cogen towards efficiency, but not totally there. So, we thought we had accounted for it before we did the project. Reality is we will have higher electrical import than we initially budgeted from the utility.
Okay. That's helpful. Thank you. Another question, and I think this, could you just describe the cogen or the boiler configuration? One of our attendants just I guess, is looking for guidance on, what the Clearway energy system is comprised of, and if you could just sort of outline that.
Yeah, I guess kind of referring back to that process diagram that I originally talked about. Basically, we have water that comes from multiple sources. Now it goes through a cleanup process. Thanks, Rob.
Yeah.
It goes through the cleanup process, microfiltration, to the softeners. Back one more, please. There you go.
Yeah.
Goes through the microfiltration, goes to the softeners existing, then goes to reverse osmosis, then goes to storage, goes through heat recovery on the direct contact, then goes to the deaerator. From the deaerator, it just goes to a single header that goes to all the boilers. So the boilers are receiving, fully treated water. And one of the things we did in the design process of this system was we initially designed this system smaller, meaning it was just going to treat the subway water plus maybe well water, and we were just going to mix it with city water. And when we looked at the operational dynamics, that was going to be hard because the middle of the night, all the plant water would be subway water, and it would be very pure. And then when the morning peak comes, we'd be blending a lot more city water. And what we said is, that's going to make a headache of a plant because you're going to have really pure water in the middle of the night and then blended water in the middle of the day, and then the afternoon you're going to have something in between. And you can imagine trying to adjust boiler blowdown and things like that with this constantly swinging water quality. So we took a pull back. We asked Clearway, we said we need more money for the project because we want to increase the size of the filtration so that it treats all the water. So now in our plant, all the water, whether it's subway, well, or even city water, it all goes through the reverse osmosis system. And what that does is it gives the plant a steady, high-quality water that they can actually operate the plant to. And hopefully that answers that question.
And the boilers are natural gas fired, just traditional
very traditional
boilers.
Yeah, they're very traditional package boilers, ranging from 50,000 pounds an hour to 100,000 pounds an hour, circa from 1955 to 1990 is their age. So even our newest is essentially an old boiler at this point.
Yes, thank you. Another question, and this relates more to the wells. Is there potential that actually digging the wells might have reduced the groundwater intrusion to the subway, or not? Maybe the aquifer is different. The subway water is groundwater, et cetera. But has there been any discovery related to doing the source well? Would that alone might that have mitigated the groundwater intrusion, or no?
No, actually, the groundwater in the well, in terms of where those waters come from, are totally different. So the groundwater going into the subway station, that's water that exists in kind of the street level down to about 40 feet. And so it's kind of very, very high in the strata. The well we drilled is actually down at 200 feet to get to the aquifer. And when we did the well, we actually put I'll call it a donut, that isolates the water above 60 feet. And the reason for that was actually sand and some other intrusions. So if you really look at it, those two sources of water are totally separate and independent.
Right. Yeah, and as I was asking the question, I was sort of drawing my own conclusion there. Not that I'm a hydrologist by any stretch. A question: do you? Let's see, I just lost it. So, Gordon, do you recall the starting chloride content of the feed water? And let's see. Sorry. And how was that addressed? Was there a high chloride content?
Chloride,
with, you know?
Yeah, chloride was not one of the major constituents of the groundwater. Interesting enough, I just got done saying that the two sources of water, groundwater for the subway and the well water, are totally different sources. But what was interesting when we were doing the initial analysis on water quality, in designing a system, you have to figure out what's your limiting factor. And chloride was not a big problem. Also, iron was not a big problem. What the big limiting factor for us was actually silica. And silica became the limiting factor for both our chemistry in the plant and also how much we'd be able to recover on the system. The reverse osmosis was actually put in with an online live silica monitor, so that one of the tweaks we made in just this week was the RO recovery changes dynamically based on the incoming water quality, and it monitors the silica and basically adjusts how much it's recovering. So it'll actually cycle from, say, 82% recovery up to maybe 91% recovery, depending on what it's seen on the inlet. And that inlet changes because, remember, it's a combination of subway water, a certain amount of well water, and in a high load condition, it's even got city water. And so that's why it actually needed to be dynamic.
Interesting. One question from the audience is yes, all of the slides and presentation will be available at conclusion, and anyone who's registered will be sent a link to access those, the recording as well as the slides themselves. Let's see, one other. I'm having a little bit of problem with my box here. So. Was there one question, Gordon? Was there much variability? Is there much temperature variability in the source water through the course of the year? Did you find that, and does that impact operations at all?
The RO is sensitive to water temperature changes. However, what we're finding from both the subway water and even more so on the well water is they're very close to fixed. In somewhere on like the 55 to 62 degree range, which is interesting because that almost perfectly matches the city water incoming temperature. So those are almost identical. And so we haven't seen a wide variance in that yet.
And let's see. Did you do a sensitivity analysis as to what the dollars per gallon of water costs? I mean, when you I know you knew that, initially you said that your water costs had increased like, 800% or 8 times over earlier costs during the time period. But you also said that of your water sewer costs, sewer was 2/3 of the cost. But when you when you were doing the calculations of, the well, were you looking at current or some future value, some escalation of water costs? Can you just kind of give us what kind of sensitivities you ran?
So when we, and to be honest with you, the sensitivities we ran were pretty, we didn't do a lot of sensitivity. And part of the reason is that on this graph is you see those water costs going up, and it's been pretty steady at 8 to 12% per year for the last 14 years, and we believe that's going to continue. And what happens is the payback ended up being so short in the 3-year time frame that essentially what happened 4 or 5 years from now wouldn't change the payback at all. Now, it would change economics, but that was kind of trying to guess in the wind. So we didn't do as much sensitivity. All we knew is that with the 3-year payback, and actually less than 3 years with the well, is that the payback was so good that it was like you can't afford not to do this project. So we didn't do as much sensitivities on that. I'll call it the big wild card in this was when we were doing the economics for the project, we were saying, okay, we're going to have subway water plus well water. At that point, we didn't have a well dug, and we didn't have well money authorized. And so, totally, what you find out if you work with hydrologists is that, well, you could get 70 gallons a minute, or you could get nothing. And so we basically went real conservative. We assumed for the project economic analysis, we assumed 70 gallons a minute for the subway and 70 gallons a minute for the well. As we've actually turned out, 70 gallons from the subway has been pretty good. It's almost like a 7 by 24 number, and we're getting close to 200 gallons a minute on the well. So that's left ourselves some hero room on that.
Yeah, very good. So one of our questioners, just to clarify, so to one of our questioners, the boilers these are natural gas-fired boilers that create steam that are used in a downtown district energy system supplying steam to 170 buildings. And then so the boilers that's what they're used for, to make steam to supply district steam to buildings. The Desalitech process is, as Gordon mentioned, a reverse osmosis. It's a proprietary design, and to that participant, we can put you in touch with them after this. Next question is 100%, Gordon, is 100% of the filtered water used only by the boilers, or are you using some of it for potable water? It's really all process use, correct?
Correct. We don't really have any sizable potable water use on site. It's
right.
Pretty much all process.
So I'm experiencing my own sort of process challenge here. Let's see. So regarding the well, are you seeing any saltwater intrusion in the well, given proximity to the bay, or has that, in monitoring the water quality, is everything okay?
Yeah, on a salinity basis, the well actually doesn't show up like seawater at all.
Right.
It's deep ground aquifer. And again, I'm not a hydrologist, and I was surprised because I was expecting a lot of chloride in that, and that's
right.
really not the case at all.
Right. And then
one of the big things I should mention on the well side that's probably made the permitting difficult. Most of you on the line may have heard of the Millennium Tower here in San Francisco, a very tall luxury condo that was built a little bit east of here, but it's in San Francisco proper. And when they built that, in essence, they didn't go to bedrock for the piling.
Right.
They decided to use something new, and what's the result is that building is leaning. It's a 40-story plus building. It's leaning. So you can imagine our challenge with trying to, and there's lots of pointing on that leaning building. What caused it? It's caused by the Transbay Terminal building. It's caused by whatever. Well, now I go to the city of San Francisco and I say, hey, I want to do a well where I'm going to be pulling water out of an aquifer, and paranoia kicks in because, oh, wait a minute, we can't have you, causing more buildings to tip over. Well, part of our permitting is going to be we have to do, ongoing monitoring of adjacent buildings and how much they're going to settle. We had to spend a lot of time with modeling, the city's modeler versus our modeler, saying, well, how much is this going to settle? And so that's one of the challenges we found with doing the first well in 40 years in San Francisco was nobody knew how to do it and nobody knew what to be scared of.
Right. Yeah, and let's be fairly litigious environment where we all live and work in these days. And so that is one of the questions that came from the audience. Did you encounter any legal issues with harvesting groundwater? I guess in addition to, kind of enhanced scrutiny and monitoring, was there much challenge in getting, a groundwater, a well source approved and permitted? Was that, how was that process?
It's been a hard process, but it's actually been somewhat close, meaning that we're working at the San Francisco, Department of Public Health, and they don't use a public process for this type of thing, again, because nobody had permitted, and I'll say maybe they didn't know they should or would, but we never had a public hearing or public comment process for our permit application to do this.
Right.
And so that probably took a lot of the way. The other thing we did with this whole project, pipeline to the subway, the construction site, is we never announced this project. We didn't do a groundbreaking PR event. And the reason is as Rob said, in San Francisco, there's a lot of, it's very litigious, and what we see happening with building developers is that as soon as they announce they're going to build something, somebody will come with an objection that says, hey, my ancestors were here and I've got rights to this. And essentially people come out of the woodwork looking for a payoff, and basically the project stops until you pay them off and they go away. Well, we didn't want that happening with our project, so we did it without announcing it. And we didn't do any public announcement until it was already in and operating. And then we had, the media splash event where the SFPUC and others could take credit for their great work, and that was fine. But that's part of the way we did the project, was by keeping a low profile.
Right. Yeah. I think there's wisdom in sort of staying below the waterline. I really apologize for that pun, Gordon. But when we were talking about this, you did mention, though, that there has been, I think, some really good recognition. The fact that this project not only, saves money, saves water, money, sewer costs for the district energy customers, your business, but you've also solved a big problem for the subway. I mean, the subway was being inundated with millions of gallons of groundwater, and so so that's been an advantage too. So can you talk a little bit about how the scale of the district energy system, your ability to implement this project, frankly, your persistence in getting it done, how has that resulted in local recognition and awareness of Clearway Energy's operation in San Francisco?
I think it's actually been pretty significant, meaning that if you took what was the public view of the district energy system, we don't have a lot of visible leaks, and so there was a lot of people who live and work in San Francisco for 30 years didn't even know there was a district steam system. And that may actually be good for you at some points. But now when this project got completed, we had Senator Scott Wiener. He came out and did, a PR moment for it. We had 3 news stations. And so that coverage didn't just bring up of, hey, there's this great water-saving project on the horizon. It also brought up of, hey, there's district energy in San Francisco. And we found that now that we have a sustainable component to our product, is that it gives us better entry into talking to new developers of new buildings, saying, hey,
right.
we can bring something to the table other than just cost-effective, reliable energy. And in fact, the success of this project has already launched our heads here, where we're thinking of another wacky idea where, we can go down the path farther with sustainability, go from the water side to the energy side, and we think we may have another project to tee up with the city of San Francisco again, so stay tuned.
Very good. So I'm just trying to clear if we had any other questions I've overlooked. So it's really all used for boiler water, energy intensity. My apologies. I'm having some technical difficulties here with my screen. And so I'm sort of flying in the fog of San Francisco. So the left.
While you're doing that, I could actually bring up one other advantage that we kind of left some hero room for in the system. As I mentioned before, using a steam system once through just softeners, a lot of alkalinity goes in the boilers. In the boilers, the alkalinity breaks down. You get CO2 mixed with your steam. You get carbonic acid corrosion in the pipeline. One of the really exciting things for us that we didn't try to quantify for corporate because the water sewer savings were already so good is this. With an RO system, you essentially remove all the alkalinity from your makeup water, which means you don't have any CO2 going out with your steam. You have almost no carbonic acid in your pipelines. What that means to our 100-year-old steam system is we're going to have a lot less corrosion in the system. So in a typical year, we repair 6 major leaks in our 10 miles of pipeline in a year. And we're expecting, just due to the better pH treatment of the system, we're expecting that number to drop from 6 maybe to 5, 4, or even 3. That's hundreds of thousands of dollars a year of maintenance that we'll be able to forego because the distribution system is essentially being treated a lot better than it was with just using simple softeners. So we didn't quantify it economically, but we think actually that may actually be the biggest win for us as a business, is that infrastructure of the distribution piping now is going to last longer.
Thanks a lot, Gordon. We're nearing 4:00, and so is there any advice that you would give to our listeners as to how to triangulate a project like this? It sounds simple now that it's all up and running, and you're kind of in the sorting out the sort of final commissioning. But working with two public entities, the city, the subway, was it important to sort of find the common ground and assess and kind of present the mutual benefits of this project to get them to pay attention and to stay attentive and to be supportive and actually, to provide funding? You said early on that this project alone helped the city hit in one big step their 2025 water saving targets. But what advice would you give someone who's looking to undertake a complicated and multi-tiered, multi-headed project like this? Did you have a big team driving it, or what were the resources needed?
It was very much a local effort. We didn't get a lot of input from the corporate office at the time. They thought this was kind of, a little Tonka toy type project. But then as it started getting, as we started showing what the economics would be, there was more support on the corporate. One of the pieces of advice I'd give to people is don't discount something because you evaluated it once it didn't make sense. This project, the concept of recovering groundwater from the subway station, we looked at this literally over 10 years ago, and it didn't make sense. With the RO technology at the time and the cost, it didn't pencil out. And then here in less than a decade, all of a sudden now the economics make sense. The subway provider was, I would say they were willing, but they weren't excited about this. And the reason is that all that water going to sewer, the 30 million gallons a year, they weren't paying any sewer cost for that. And when we talked to them and when we talked to the city of San Francisco, nobody could explain why there wasn't a sewer charge. But there hadn't been one. It was some maybe handshake deal back in the 60s. But they didn't have the economic incentive. But they were very willing partners. Like when we said, hey, we need bigger pumps in your cistern to get the water to a plant, they basically said, well, if you provide us the pumps, we'll put them in. So we provided the pumps, they put them in. And then we had asked the question, do you have enough electrical for the bigger pumps? They said, oh, yeah, we got plenty of electrical. Well, we put the pumps in, and a month later they're saying, well, turns out our electrical's not enough. If you'll give us the parts, we'll install them to upgrade our electrical. So they were very, very great partner. But when we did the PR event, they didn't actually want to come because they were worried about other implications in their public view. So they didn't come along. But it was what you said, Rob. It was working three-way, finding at least a neutral and hopefully a win for everybody on it. And that you just got to stick with it.
Yeah, I mean, oftentimes you find on the other side of the table, or sort of colleagues like this, that people really are motivated to do the right thing. And if in the case they didn't really have an avoided cost, right, because they weren't paying for sewer charges, that might have actually been a little bit embarrassing and maybe a reason why they kind of preferred anonymity. But in fact, I think things like this. Common sense, mutually beneficial projects. It's good when they see the light of day, and even better when they're recognized. Cheryl, could you just advance the slides so I can I want to again thank Gordon for the presentation today, and as we mentioned, the slides will be available both as streaming, so you'll be able to listen or share this webinar with colleagues, send them a link, and they'll be able to see the process. Back up one, if you would, Cheryl. Or did you go? All right. So you'll get. So I'm not able. Okay. Advance one. So the Innovation Award, again, the applications for the 2020 Innovation Award are now available. Those of you who are participants, members of IDA, we'd love to hear your stories, see projects. They don't have to be, sort of the scale of what Gordon and his team have accomplished in San Francisco, but I would suggest, have a look at the link, IDEA Innovation Award on our website, districtenergy.org, and I think you'll find both historically some really great projects, but we'd love to hear from those of you on the call, innovations that you're considering or have implemented recently. Next slide, Cheryl. Thank you again for participating. There'll be a brief survey to conclude. If you would, just take a minute to fill that out. As I said earlier, you'll get an email with the links to the presentation, so you'll be able to share the slides and the streaming. Next week, basically same time, next Wednesday, November 6th, we'll be doing another IDA sustaining sponsor webinar with Train, where they'll talk about renewables procurement and some new ways to think about increasing your sustainability modeling and really sort of driving integration of renewables. You won't want to miss that. Again, it's a free webinar provided by IDEA on behalf of our sustaining sponsors. For those of you on the call, if you're interested in becoming a sustaining sponsor of IDEA, please log on to districtenergy.org, our membership services sponsorship page. All the information is there. If you'd like, please give me a call at 508-366-9339. Happy to help you understand how IDEA can help bring visibility to your business, your projects, and the good work that you're doing. I think, Cheryl, is that our concluding slide? Nope. So I'd like to, shameless plug, invite you all to join us next February at our Campus Energy Conference 2020 in downtown Denver. Program is set. You can see the technical details, again, at districtenergy.org, Campus Energy 2020. Last year, this conference was held in New Orleans. We had nearly 1,100 people attend. I'd urge those of you who are thinking about it, please register early or register soon. The early bird rate expires in a couple of weeks, November 15, and also urge you to secure your hotel as, space goes quickly. And we're certain this will be, there's over, I think, nearly 200 presenters involved in this conference, 120 plus exhibitors. We really think it'll be a great venue and hope to see you there. And then next slide, Cheryl, is our IDEA 2020. Our annual conference will be Washington, D.C., June 22 through 25. New Vision for District Energy. The call for papers is still open. So if you have something you'd like to present to our attendees from around the world, please visit our website, IDEA, districtenergy.org, IDEA 2020, and we'd be happy to receive an abstract with you. Just bear in mind we have historically had twice as many abstracts as speaking opportunities, so if you're at all interested, I'd urge you to submit soon. So that's all we had for now. I want to again thank Gordon Judd from Clearway Energy. Congratulations, Gordon, on a terrific project. We really appreciate you making time to share the nuts and bolts of it with our guests. And for those of you, in addition to the webinar slides, Gordon did present on this at our annual conference this past June in Pittsburgh. So all the proceedings are there. You can see this presentation as well as many others at districtenergy.org, our proceedings page. All of it is there for your viewing. So, Gordon, any last words before we sign off?
The only word I would say is that if you've got some techno detail that you just didn't want to ask as part of this webinar, feel free to reach out to me at gordon.judd@clearwayenergy.com, and I'd be happy to correspond with you individually.
That's great. We certainly appreciate that, Gordon. And, I think the peer exchange is the #1 reason people are members of IDEA. And really, I want to thank you for, being available to our guests and to our industry and sharing the great work you've done in San Francisco. So I'm going to bring this to a close. Thank you again. And Gordon, on behalf of all of your friends and colleagues here at IDA, hoping that the wildfires and really sort of frightening conditions in California abate soon, and you and yours are safe and sound. And again, look forward to seeing you. Thank you all for attending. And if you have any questions or need further assistance, please reach out to idea@districtenergy.org. We'll do the best we can to help you. So thanks, and happy Halloween, everybody. Thanks again, Gordon.
Thank you.